Well, hi everybody. Can you hear me there, in the corners? Can you hear me over there? Yeah? Cool. I'm Fanta. I'm teaching this workshop today, GLSL Intermediate somehow. We're going to focus on Raymarching a little bit because I figure it was a topic that is not much cover in the internet and stuff, and also because we use it to create um, um, the image of the workshop of the summit. You've seen all this fluffy thing around that was created with a Raymarching algorithm inside TouchDesigner, right? Um, so what I do, I'm a freelance developer and designer based in Berlin. I'm from South Spain, and I had a background in environmental science. But then the financial crisis came, and what I was doing for fun was VJing. So I said, okay, let's try that way. Moved to Berlin, start to VJ, and then got deep into the craziness of doing visuals and the real time madness that I really like right now. Um, yeah, maybe we can introduce shortly each one of us. I'm just said, yeah, what I'm doing and what I want to get out of this workshop is, well, getting to know all of you, of course, and also that if there's this tiny concept that you get, not how to do the remarching, but why is in that way done and why it's important. If any of you will get that concept, then I'll be happy. That will be my goal for the workshop. Cool. Thank you, everybody. I see a couple of trends. So there's the VJ kind of direction people and some others that are coming more from the technical side. Don't get lost in the detail. Just try to follow along, and I will come if I have time individually to all of you and try to push each of you to the same level. Have you all of you received my email about checking a little bit the book of shaders? Meaning, well, the question will be actually, have you tried shaders before? Do you know what they are? To write a little bit the syntaxes, all of that. Is anybody that done? Yeah, cool. Oh, that's fantastic. So let's get into the topic. That's my Instagram, and I'm sharing there some shader experiments that I do, and there's a few of them that are Raymarch algorithms. That's how I enter into the topic. Like before I knew about it, I checked them, used them, but I didn't really understand what was about the whole thing. So I just learned by myself how to create those blobby shapes. That's the common thing that you do in Raymarch, right? So what is all of the thing, all of the fuss about? Well, the idea here is that you create something that looks like 3D, but it doesn't contain any vertex. Doesn't contain vertices. So it's not a 3D model. It's actually just a mathematical representation of a surface. And with that, you can, let's say, fake lighting, so it looks like it's a 3D shape. Okay, that's the trick. That's why we use it. Because when you work with vertices to get smooth transitions between vertices, you have to create more vertices to be able to make those um, this kind of stuff, right? Like if you wanna, it doesn't play. Sorry, I just realized that this thing doesn't play on a second screen. I don't know why. You can see it here, but not there. But to create those blobby thingies with vertices, you will have to have a lot of them. That will take your memory down, your processing down, and in SOPs, forget it, right? So that's why we have this technique that was invented many, many years ago. And the basics of it is that you see there, that is in German, sorry, I didn't realize till now. But anyway, camera is camera, right? So, so what you do is create a camera that for us is just a point in space. It's not more than that. It's just three coordinates in space from where you throw rays. That's where the ray part of Raymarching comes. You throw rays to every pixel of your screen that you want to draw, and those rays hit or not hit anything. If they hit, we check different things of that position in space. If they don't hit, we just, let's say we paint it black, right? So we have these three elements. We have a camera that is just a point in space. We have, well, four elements. We have our pixel, that's our layer. No, not layer. That's German. Our raster, our iteration, our loop, from where we take for every pixel one ray. Then we have our 3D model, our world, where we're drawing a sphere, and then we can have lights or whatever. And then the marching part of the Raymarching word comes from this concept. We are throwing a ray, right, from the camera to the pixel and beyond. So we see what's behind that pixel. That's an important concept. We throw to the pixel, and then whatever we find beyond. But to count every single millimeter, let's say there, it's expensive. So what we do is march in steps. And for every step, we check our world. If we collide with anything, that's what we want, to collide with something, then we give a value. But how much we go is easy to test, because a distance is, the distance function is built in GLSL, so it's very cheap to calculate. So we can always check distances for not for free, but very cheap. So for example, we have this shape that is defined by our formula. We have our point, so we test. How far are we to the shape? This far, that's the length. So we move until there. That's our march, first march. And then we test again. How far are we? Here. So then that means that I can move that amount, this amount, without hitting anything. Did you get that concept? I'm going a little bit fast, but if you have questions, ask right now. It's a good moment. So I don't hit anything. I know that this distance, I'm hitting something, right? But the start is the camera. You measure against your shape. You have one shape. I mean, we are going to start with one shape, but at the end of the day, one or many is the same behind the scenes. Okay, we are going to start with one shape, but is shape or surface is the same concept for us right now.
But you're just trying to find the distance to the nearest thing as that first step. Is that the idea? So
yes.
The point on the shape that's the closest.
Yeah.
Becomes the first distance that you're checking.
Exactly, because I know that if I move in any direction, I won't hit anything until there. But my direction is not that one. For this ray, for this pixel, is this one. But I know, because I just test, that there's nothing at that distance from me, from that point, from the camera right now. Okay? It's a formula. Yeah. So we are going to define formulas for each shape that comes in a second, and then we can combine them into just one big formula. That will happen. I mean, you don't have to take care of that. We are just going to see some tricks, how to combine shapes, how to make shapes in different positions, all of that. But at the end of the day, I just have one value to test against, one surface. Say it again. Sorry. Yeah, because I'm testing for each pixel in the screen. So what I want to do is to draw that formula. The formula is there, but I want to draw it on the screen. So I have to test for every pixel how this pixel relates to the formula, to the surface. Let's call it surface from now on. Okay? Does it make sense? I know it's a little bit abstract right now, but we will see it in code. So that's the thing. Length is cheap. So instead of marching every single little step, in this way we're going to march 1, 2, 3, 4, 5, 6, 7 times instead of every 0.5 that will march many times that we have to check against the surface, and that will be more expensive. As opposite to ray tracing that works in a different way. That's the essential part of Raymarching. We have a point, there's the camera, from where we throw rays to the pixel, and we test beyond the pixel what's in there, right? And we do it with that optimization that is a march. Yeah? Yeah. In this point, this is the origin of my camera, let's say. I check my distance to the shape, and I know that this is the closest point. That means in the direction of my pixel, that is this one, I can move freely this radius without hitting anything. And then I can check again how far I am. And I check, this is the closest point, so I can move that radius again freely without hitting. So I understand that I'm not hitting anything, so I don't have to represent any value. My pixel still doesn't have any value to represent because I'm not hitting anything until I get there. But I optimize already the process of getting there by checking these distances and moving in not consecutive steps. Yeah. Well, no, it doesn't depend on the scene. It depends on the amount of rays or amount of steps that you want to check. That's the limiting point because that's inside of a loop. Yeah. The amount of shapes that we have doesn't impact, well, I mean, it does, but not in the same correlation that the amount of steps. The amount of steps is your bottleneck somehow. So there's ways later on also to optimize that. But yeah, that will be your focus point. Yeah, along the ray. Yeah, that's the concept. You march along the ray in steps that are not regular. Having different shapes is costly, but having the same shape repeated many times, that's free, for example. Almost, yeah. Okay. Questions there before we get into coding? Good? Is the concept clear? We have a camera here that is a 3D thingy, but as I said, it's just a point. That's a point in space. You see all the rays come from the same spot. We have a representation of the pixels, but at the end of the day, pixel is also a point that we get through the UV of the texture we are looking at. And then we have the shape itself. Okay, so then let's get into it. It's going to open eventually. Cool, let's get rid of that. And then, as I said, this is all happening in a fragment shader, so we just need a GLSL top. Right? One note here. If you're running the last version, there's an issue with the saving external files, so I will go with taking care if you're using Sublime or VS Code or anything like that, because sometimes get disconnected. So you have to save and then close Sublime and then open it again, stuff like that. So bear in mind that, because that was introduced like a couple of days ago and it's not yet patched. Sadly, was yeah. Exactly. So make sure that this guy and this guy are the same. And if they don't, just close it up and open a new one. So you all have your preferred prefer editor. If not, you can, edit here directly. That's also fine. So let's get into it. So the first thing we need to do, as we said, is to define a camera. So I will say that my vector 3 ray origin equals um, 0, 1 in y, and then I don't know what do I have here. This is going to be a little bit of a mess actually. -2. So I put it a little bit back in y, right? We are imagining a point in space right now, and those are the coordinates. So it's 0 in x, 0 in y, but it's a little bit backwards, right? And then we need ray direction. Where are we throwing our ray to? So that will be another vec3, my ray direction, and it's going to equals so basically it's the UV, right? But it has to be in 3D. So we say that is UV, that is a vec3 composed of my UV and C1 for C. But I didn't declare my UV, of course. Vec2 UV equals, you all know this one, if not, just ask. VUVST times 2 minus 1 to center our coordinate system, right? Anybody has a question about those 3 lines right now? And we have to normalize this to make it work, actually. Yeah.
Why is the redirection based on the UV?
As I said at the beginning, we need to throw our rays for each pixel. So we need to know where am I right now. So my position, the position of this pixel, is actually the UV. So yeah. So that will be 0, 0. That will be 1, 1 if we're looking from the camera perspective, but we multiply it by 2, subtract 1, so we are now at 0 in the center. 1, 1 minus 1, 1, right? Do you all feel comfortable with these 3 lines? We just defining a point, that we say that that's our camera, from where we're going to throw rays. Where? What's the direction? To the pixel. So that's the UV, and we need to normalize it, but yeah, the UV basically. Okay, and now we start with the Raymarching. We need to define a distance from the origin. That's what we are calculating, right? Origin. And that's going to be at the beginning, it's going to be 0. Meaning we are in the camera. Origin is camera, the initial distance is 0. That's the step we're going to march. Right now it's 0, and then we start to march. We need, as we said, a loop for it. So let's create one. For int I equals 0. How did I call this one? E minus. How many times are we looping? So we have to define how many times do my ray can march. So here, sorry, in the other picture, we were marching until we hit something, but we can that will be an infinite loop. We have to close the loop and say, if after 10 march you didn't hit anything, then let's say you're not going to hit anything. In that sense, we're defining a space in 3D that we can render, right? Huh? If there's none, we just say black. We didn't hit anything.
So it's like making a far clip in
Kind of, yeah, yeah. You're just saying, hey, don't march forever. Just stop at some point, because if not, we'll just, yeah, it's going to burn the graphic card. I don't know. What do I have here? 128. And then increment that, okay? So this is our marching loop. So we have the distance from origin that we're starting, that is 0. Then we're going to march as many times as needed, up to 128 right now. Okay, and then we start to march. And that's the next position, or next, yeah, position. It's the ray origin. Oh man, I'm really. The ray origin plus the distance from origin that we had already from the previous one, right? That is 0 for the first iteration, times the ray direction. That will be the position in the next, in every step, that in every march that we do. Yeah.
Just wondering, is it necessary to like every time create a new variable for every step, or
You mean
not like have before the for loop have like this all vector-free position, initialize it as a 0, 0, 0, and then just override it?
it's not going to make a big difference, but I mean that's almost a philosophical question, like memory instead of computation. You can choose. I mean, for this one, doesn't make a big of a difference. But yeah, I mean, that's the question. Do you want to use more memory? Do you want to use more computation? For a vec3 like that in a shader, doesn't make a big difference. Yeah, because you're going to just move the memory around. So it's not a biggie. Yeah.
Why ray origin and distance origin are two separate things? Where, because basically this is the point where the camera is.
Yeah. Ray origin is this one plus distance from origin that in the first march is 0. That means here. The second march, distance origin, we're going to write it now, okay? So it will be this one. We didn't write it, but what we're going to do is create that distance. We're going to check against the formula, so then we can add that for the next step. I'm going to write it and then we discuss it. But it will make sense in a second. So we have our ray origin and our distance origin. Right now we are in the first iteration, let's say, so we are at 0, and it multiplies by the direction, so it's that direction, right? So we're going to that pixel. What we need to do now is test against the map, against the world. So we're going to make the simple world right now that is a sphere. So let's say float sphere equals length of the position we're at minus 1. So that's how you define a sphere in Raymarching. It's a very easy one. So you just checking the distance around that point, around a point. And then that step that was this adding to the distance origin, the the scene. That right now the scene is just a sphere. Let's change the name of that for a second. Float map equals, right now we just have a sphere, map meaning the world. Okay. And now we optimize with this idea in mind, right? If well, we don't optimize right now. Let's keep it for a second later, so we have a clear idea of what we're doing. So this is the our Raymarching step, and then we are marching, and then we return the distance. That's it. I'm writing it a little bit different, so bear with me. So vector color has to be the distance from origin. I hope this works. We're seeing all white because the distance is 2, so I have to divide the distance by 2. One second. Uh, that should be fine. I'm going to open the original file and maybe we go through it together. Ah, yeah. You guys have something similar to that one? Yeah. So the distance origin here divided by 2 was because our camera is 2 units apart, far from the camera. So, so then we saw everything. We are just showing distance right now, so we were seeing everything as full distance. So it's a matter of what we can represent as pixel. The distance was there, we couldn't see it. Yeah. Yeah, that's doing nothing. It's just a naming convention right now. Just because, yeah, we're not showing, yeah, because it's a sphere right now only, but then later on it will be a map of the world. So we will have more than just one sphere. Okay, ask me questions. So also I can put myself in the right clear mind because right now I have a mess in my head. Yeah. So we couldn't see the map. It was there, but the values were all above 1 because we're not doing lighting, we're just showing the depth map somehow. So the depth map can go way beyond 1, but as pixels we can only show from 0 to 1, right? So I had to divide by the distance of the camera to be able to see the depth map as color. So that was a little trick because we are working in a bare bones Raymarching that is not proper right now. Oh, yeah, exactly. And if our camera is at -4, then we have to do it divided by 4 to be able to see our sphere. I'm just adjusting the values of the pixel column, not the distance itself. So what I'm representing here, not very exciting, but what's happening behind the scenes is that we have a sphere. We don't have a light right now, but we are throwing rays um, from the camera to every pixel until something happens. One optimization that we can do right now, we did this optimization. So step as many times until 128. Another thing we can do is don't go beyond, I don't know, let's say 1,000, the far and the near planes, right? Don't go beyond 1,000 units because I know that I'm not going to place anything there. My sphere is not there. I'm not going to have a background, nothing. So I can just start to cut and optimize a little bit our code. that happens here. So we can say if the distance seen, how did I call it? Distance origin. Distance origin. It's smaller than, for example, 0.1 or 0.001. That will be our clear near plane, or distance origin. It's bigger than 100 units, then break. Break the loop, because, yeah, that's it. You don't need to go further. Yeah, that makes sense. Now you can try to move the camera around, for example, and see what happens. So if I move my camera to 0, my sphere is center. If I move it to 2, then you see that it's an oval, because there's perspective already there. If I move it closer, as I had it before, and I adjust my depth, then it's bigger. So what we are showing there is the distance from the origin, meaning the depth. Do you see that? We are not showing the sphere itself. Let me do one thing so we have the alpha in order. Um, vec3 shape equals distance origin times vector 3 1, meaning, oh, that's white. Okay, and then we do shape 1, so we have a solid. We got rid of this alpha thingy. Did you follow that one? That was just for the coloring. So what we are representing right now, what you can see is the distance from the origin, meaning where is this ray hitting. The background is white because it goes beyond 1. The distance is really big, so the value is high, and in color that means white. It's probably clipped. It's more than 1. And the gray values meaning closer to the camera. That's a depth image. And that's going to be useful later at the end of the workshop when we mix Raymarching shapes with SOPs, because we can take the depth of our Raymarching and combine it with the depth of the SOPs, and we can have 3D scenes that combine SOPs and Raymarching. Hopefully we get there and I don't collapse. Okay, so let's go through it one more time. We have our UV. That's the position of the pixel. As the first line. We get the UV from touch. We scale it and reposition to our needs. That is with the 0 in the center. That's something it's easier to work somehow. If you have the 0 in the corner, then it's always weird. So 0 in the center of the screen, 1.1 minus 1.1 in the corners, right? Then we have our ray origin. That's our camera from where we throw rays. In real life, it's the opposite, right? You get the light, hits things, and then the camera get those rays. But that will be impossible to calculate. So what we do is the opposite. What the camera sees is the only thing that we are calculating. So we throw the rays from the camera to the pixel, and then we check. So the first pixel here at the top, the ray went there, started to march, and hit nothing. So we have a value of probably 100. That's our far clip, right? Hit nothing. Then the next pixel. Let's say this pixel here. That pixel, we throw the ray. It march once one, distance origin 0, ray origin is 0, plus 0, 0 times 0. And then we check the length, so our sphere, we check it, and we add that to the distance origin. That sphere check that we did is going to tell us where we can march next, right? So it's probably already the sphere. Imagine a sphere here. So it's probably already that one. Because 0, 0, that will be the closest point. And we just then put that value into the distance origin. Clear? I see some faces like, yeah, clear, but not really. That it's a really easy one. Let's look at it in 2D because it's easier to see. So if I have this shader here, and like always, I define my UV space that will be vuv.st times 2 minus 1. And then I show the distance of my UV to the point 0. This is what I got. What happened? Oh, yeah, sorry. That has to be a vec 2, of course. 0, 0. So the distance of a point to another point can be a circle in that way. Well, it's a field. It's not a circle itself, but we can use it to create a sphere in 3D or a circle in 2D. If I, like we did this morning, step this, float distance field equals that, and then float step equals what did I do? The step at 0.5 of the distance field, and we show that that cannot be step. That should be step this. and we show that, then we have a circle. That's the same concept applied to 3D.
And so sphere is just a built-in primitive in GLSL, or
No, we're making it with a very simple technique. There's just one line. There's this one here, right? We set the length of the position, basically. Similar to that one that we just. It's a very cheap way to do it. Okay. So we're just showing depth right now. We're not doing any shading to it. We're just showing how much did my ray march in space. And this is, as I said, a value that is not from 0 to 1, so it's not a pixel, so it's not something that we can show easily. So that's why we needed that one line. There's just a little hack, right? To be able to show them depth as image. Now the next step will be to really create color and put some color to that image. I mean, we can fake, of course. We can say that we are going to take the depth and we are going to colorize it. So instead of 0.1 that we have, 0.3, 0.0, 0.9, and then we have some color. But that's not the, this is just a fake colorization of the depth. So we're going to do the right thing. And for that, I need another one. I'm going to save this one. I'm going to go and make some files that I can share with you afterwards because I have all your mails. So I'm going to send it to you. Documents, course, GLSL, 1 and 2. This is 0, 1. So the next thing will be, for example, to create 2 spheres. So instead of having just one thing, we can have many of them. So what I'm going to do is bring that out. And I'm going to say that I'm going to have a, no, it's a float function called map. And wherever I place there, that's going to be my representation of the world. Right? And right now, I need, of course, the position I'm at. And then I'm just going to bring this one in. And make a return. Return to it. Of course, now it's P. This one. And now map is going to equals map position, right? So I'm just rearranging a little bit things. The next thing I'm going to rearrange is to declare some constants for these guys here. Okay? So we can read better what's going on. Yeah. Equals. So I'm going to make some defines here. And I'm going to define 128. That will be my max steps, right? So my loop that was going to to 128 now is going to go to max steps. So that's just an easier way to read things. I'm going to make a new one for this guy over here, 001, and that's going to be the minimum distance that I'm going to march. My marching sphere, this one, cannot be smaller than 001. And then, I'm going to define the same for a max distance. And that's going to be 100, we said. And now we can place those guys here and there, right? Up. What did I do? Undefined. Ah, yeah. Thank you. Yeah. Yeah. That was just beautifying the code a little bit because it's going to get messy soon. So now we have the most basic Raymarching shader you can write. That's the bare bones of it. That's the really minimum. Is that clear? Is that you have still questions? Why is max steps 128? Are we? Why do we have to give the position to the map? All that stuff.
P is just a built-in function.
Say it again.
P, that's just a built-in function. Like, where is this coming from?
P, we're giving it to it later. We're saying position. So I'm changing it here, and then map P, that will be my position. Yeah? So again, I have my march step. And then when I'm there in the next march step in that direction, I check against my map for this position. And I say, hey, how far I am from that from the map. Then it gives me that position, and then I march. Right? And at the end of the algorithm, I have the distance that that ray marched all over the loop. And that's what I'm going to use. Right now, I'm just showing it as a depth, but what I'm going to do is with that point, calculate the normals of my map. So I'm going to check again the map, but now calculating normals. And to calculate normals, there's already, where am I? I have a gist, if you can go and copy that one, because that's a function that hasn't been changed in the last years. This is like a standard thing. There was a guy that optimized it a little bit by using just one vector 2 and then making this Switzerland. But it's the same function that we had since ever. So we just copy it. And what it does is you check that ray in that position, but you also check a little bit above, a little bit below. So you can say what's the derivative of that shape in that position. So you can get the angle, right, on that point. Or the normal, yeah. Not the angle, but the normal. That's why it's called get normal. So I'm just going to copy that one. Did you all get the it's my gist? Thomas gist.github.com/Thomas VanTa, and then the last one that is there. Going to copy that one and bring it here. So one more is this address. Can you see what I'm? Yeah, you don't see. gist.github.com/Thomas Fantas in here. I'm gonna go around then. You have it? Yeah. You have it all good here. Okay. Do you all have it? Let me try one thing. Let me see if I can show just the normal without any lighting. Huh. Yeah. Okay, what I did here, apart from breaking it, is to try to show only the normals, right? So I created an empty vector tree. I populated inside my loop with the position, and then forget about the background. Um, the sphere you can see in your screen better than there, but this is green and this is red. So we are able right now to calculate the normal of that sphere. And we are going to use that to ray cast another point to a light. I mean, it's not really a ray cast, it's just a dot, but yeah, direct the light in that normal. So where that light hits. So I'm going to save that as a funky, funny thing. Or intermediate step before getting into them.
Can you scroll up to where you added the normal
Yes.
stuff?
So I just copy my function outside of main. So I have a function that I can use. And then I created an empty vector outside of the loop. And then I populated it with my function in the position of the march step that I'm at. Yeah. And as I said, I'm sending you guys all these files later via email, so you all have it.
So I'm still not seeing the 4 quadrants of color.
Okay. What I did is multiplying my distance by the normal. So before I had here an empty a vector 1, now I have my normal. And you see in your screen, because there I don't see, I don't know if you can, but this is green and this is red. So we have right now valid normals. Is it a good moment for a 5 minutes break? For me, it is, at least. Well, let's take advantage that it's really noisy in the space and continue with our shaders. Do you hear me at all over there? Cool. Let's go farther, a little more step into it. Is everything so far understandable? At least, more or less, we're in the flow. We know what we're doing, more or less, the direction. As I said, even for me, I miss some of the math that is behind that, but we know how to use it. We know how to calculate dots, why the normal is showing up. We know all that stuff right now. So the next step, now that we have depth and that we have normals, will be to add some shading. And finally, the word shader will make sense. That's because we're going to use that program to create some shades and lights in our scene. So that's the next step. After that, we're going to take a look at how to have something more interesting than a sphere in the center of an empty space. And after that, we're going to take a look at how to make deformations to space, how to twist that sphere around, how to make it noisier, because that's the eye candy that should come at the end of the workshop always and be interesting for the picture. Yeah. Um, mm, um, I think, I mean, I don't really, I couldn't explain it to you, how to say, scientifically, to telling you exactly why. And I'm going to spend a lot of time with that. And it's not really interesting. Like what we said before, or what we looked before, if we take that one out, we get rid of it, for example. So what you show, what you see there is part of the steps. You can see in these lines the marching steps almost, because this is just a trick that we made in the moment to visualize the normals, but it's not the correct way of visualizing normals. That's how you are going to use it, but it's not how you should visualize normals. So let's focus on the other stuff, because also, yeah, my energy is limited today. So what we're going to do is calculate a diffuse lighting system. So it's easier or simpler than a fong that you know that is like the simplest material. So we are going to just calculate the diffuse part of the fong system. Okay, so we're just going to calculate one light, how that light illuminates the scene. We are going to still work with one sphere. Okay? So what we're going to do is, of course, create a new function. And then after this one, we are going to reorganize our code once more. So the new function is going to return a float, and we're going to call it diffuse lighting. And it has a vec3 position as well as a parameter. We are going to declare our light position here inside just for a second, so it's clear what we're doing and we can see everything together. So this is going to be our light position, and it's going to equals whatever. So we are just going to position it in space, put it wherever you want. I'm going to say that is at 0, 5 in Y and 6 in Z. Again, once more, just a point in space. It's not a light per se, it's just a point. We want to direct lights and calculate, direct rays and calculate a value at the end of the day. That will be the value of how much light is affecting that point of the map in space. What we need there is to normalize the direction of normalize the direction of my light position minus, so that's from one to the other, P. That's my sampling point. Do you get that one? That's to go from my point in the surface, whatever I'm sampling, to the light. You do that with subtracting vectors, right? Then we want the normal. Let me recall this light so it's clear. We call this normal, and that's going to be the one we used before, get normal at P. Right? I have these two elements, and then I'm going to do a little trick that is getting the difference. So the diffuse, sorry. Diffuse equals, let's leave that for a second, the dot product of normal and light So if we take a look at what's the dot product, is the angle, basically, right? So what we're getting is the amount calculated as an angle of the normal to the light. So that's a that's basically the easiest lighting you can do. And before we can show that, we need to clamp it because we are now in the color world. So we need to clamp that value between 0 and 1. That's saturate the value in GLSL. And we return it, of course, we need it back. return diffuse. Yeah? Is that function clear? Just we have one more element, right? We had the point in space, we had the normal of that point. Now we're adding a light somewhere. There's another point. If you remember that one, so this is the direction we're calculating now, that angle. And then we can use it. Diffuse lighting P. What did I do? Ah, sorry, yeah, of course. We're changing what we had as normal as diffuse, and then we should get that inside of them. Should we get it inside, actually? I don't think we, well, let's try to see how it breaks. 63. This is a float, of course. 70, it's broken. Peg 3 shape is equals to peg 3. Diffuse. Yeah. It's really broken. 1 second. That can be my position. Yeah. So my light was way behind the sphere, so I couldn't see it. So I'm going to put it to -2. So now it's in front. Are you guys there? And I'm going to change the resolution of my top to 1K so I can see something a little bit nicer. Yes.
So I noticed the sphere is still a little jagged on the edges.
Yeah.
If you want to alias that, do we have to change the SDF at all, or is that?
Not the SDF, but how you sample, because we're sampling one per pixel, one ray per pixel. So the way to go there will be to send, and that's where 2x anti-alias comes from, 2 times per pixel array, for example, or 4 times. But then it gets exponentially more expensive.
Yeah, that makes sense.
Yeah. But for now, for example, what I did was changing the resolution of the top to 1024 by 1024, 1K, and then we have something nicer. Yeah? So now, that was very German, yeah? Yeah, yeah, diffuse is a float. And then we did this here as vector 3 diffuse, but what we can do is actually do it correctly. So we have a vector 3 that is 1, 0, 0.5. So now we can color our light. So you can bring that one out. For example, that will be diffuse color. You multiply by diffuse value, and then you get, yeah. Now it's only for one light, but yeah. I'm going to make a change to the map. So we're starting to see new shapes. So this one is a float sphere equals this one. And now return sphere. That shouldn't break anything. Didn't break anything. But now I can add something else. For example, the easiest of the easiest is a plane. At 0. And here gets interesting. How do we combine shapes? There's many ways. The regular way is using the minimum of the sphere and the plane. Or the max. No, that's the combination, so it's the mean. Are we at 0 in our camera? Yeah. So that's a little issue that we have many times. At 0, 0, we get strange results. To position my sphere, right now is at 0, 0, 0. We can do this. That is the position of the world minus where I want to locate it. So 0, 1, 0, for example. Now my sphere is floating. Yeah? Are you following? Yeah? Nice. Yeah, doesn't have to be called shape anymore. But yeah. I'm going to save this. Yes, 1 second. I'm going to save this one to the map function. So now we have two primitives somehow that we can combine. From, yeah. Minus, that's moving the sphere. Yeah, sphere position, yeah. So for example, if I move it to the X a little bit, now easily I can copy this one and make another sphere, sphere 2. I'm going to move it to the other side and a little bit to the front, right? I made the second sphere. Now I'm not showing it yet because it's not here. So what I can do is create a new float that's going to be called spheres, very simple. And as we said, mean will be the easiest. Sphere, sphere 2. Well, this one should be called 1 right now. It's the worst naming ever, but yeah, follow me. And now spheres here. Yeah, that should be fine. Is your camera at 000? Move it up in Y a little bit. Yeah, yeah, yeah. So now we have, it's not working. One thing I did really quick, it was to move my camera in Y up a little bit because there's strange issues sometimes at 0. So I move my camera up. If you all have the, I see a lot of red and blue. It's fine. It up, yeah, yeah, yeah,
Sorry, I don't see my normal map.
yeah,
Everything is black. I don't see
yeah. Move the camera.
camera.
Oh no, you have it up. The ray origin. Mm, your light position is fine. Can I see the end of the main? Times diffuse. That should be okay. Uh, your diffuse.
Here.
Yeah, where does it get calculated? I think you're missing that one. Yeah, inside the main, you should call diffuse lighting position. I'm going to show you the bit of code that I'm talking about. Here, I think you're missing that one. Yeah. Okay. So I guess you already started, but you can play with the function that combines the shapes. So instead of min, you have max. What you have is the intersection of the two shapes. So if I move this one back a little bit, you see so that's where the space that the two balls collide. Then you could do minus sphere 1, sphere 2, or the other way around maybe, so we can see. And that's 1 minus the other. And that's really powerful. I don't know if you tried the SOP that does that. It's like killing your CPU. Yeah. Yeah. I think that you have the normal multiplied by the diffuse lighting somewhere, maybe. Yeah, no, that looks good. Mm. Did you take the map out? Yeah, it looks like the bit. Yeah, it's a function now outside the loop. Yeah, I think it's that one.
I don't know why mine is weird. I just compared code with him. It looks pretty
Hmm.
much the same. No errors, but it obviously is rendering totally different.
Yeah. Do you have your map outside? Yeah, and then are you calling that map function inside the loop? Map equals sphere. Yeah. That bit over there. Map equals map position. Because now we got it out. Yeah. If if you see some bending and we're rendering, check if you're calling the map function that now we put outside of the loop. You're calling the map, that's good. And your lighting, move the camera maybe a little bit up. The ray origin. Yeah, move it in Y, move it to 1. Yeah, that's an issue. Oh, okay. No, that's fine. That looks good. That shouldn't be an issue, no? Mm. Map is map position, distance plus map. That looks all good. Distance origin. Can I see the map then? One zero one zero 5 minus. Yeah, maybe they are not colliding. Try to put sphere and sphere 2 without the minus in the mean. No. So the positions were off and they were never colliding. So you were doing an operation on something that was not colliding, so you couldn't see it because there was nothing. And I think you have your map shouldn't be sphere anymore. Now you can call map position. Hmm. Maybe the light is behind the sphere, so you don't see it. Is everybody having results? Some sort of? Um, we can check in Inigo. Do you guys know Inigo? Or maybe, well, um, let's do one of these. So everybody, yeah, let's do it together. Inigo, Inigo. I'll show it in a bit. Yeah. So what we are going to do quick is to show how to make uniforms so we can control aspects of the thin of line. So what I'm going to do is define. Do you hear me? I feel like nobody. Do you hear me over there? Yeah. It's hard. Okay, I'll go a little bit up. Now, what I'm going to do is define an uniform. That means variable that I can use from outside the shader to control parts of the shaders inside. So what I'm going to do is having defined a so-called uniform that I can use in TouchDesigner and get passed to the shader. So I'm going to go with a vector 3, and I'm going to call it position sphere. Which one is this one? 2, whatever. Uniform vector 3 position, and that now I can use. But before I can use it, I have to define it in my top, in my GLSL top, in the tab vectors 1. I have to call it the same way. So I'm going to copy, paste, and just for a second, I'm going to copy these values as well, so I'm in the same. I can see the same and not get weirded out by strange values. 1.25, right? Everybody follow that one? It's a uniform. It's called uniform because it has the same value for all the pixels of the frame. And now I can use that one here, right? Have you seen that one? I had these values. Now I copied them in there. I call my uniform name in vectors 1 position sphere 2. I declare it inside my pixel shader, and then I can use it. Save. I should see the same, which is the case. And now I'm going to go to TouchDesigner for a second and play some LFOs. Oh yeah, have some fun, exactly. So my Z value, I want it to go from minus 0.125 to positive 125. So I'm declaring my, I'm setting the amplitude of my LFO to that value. And then I export that one as a reference. So now my sphere 2, that is basically invisible, moves in Y. So that will be the way to go to make all of the parameters available outside of the shader. So let's leave it for a moment after. So I'm going to explain a couple of more things, and then we can play with the system so you can export, create all your uniforms, and make crazy shit. That is at the end what we're doing. Yeah, that's the important part. Right? It grew. We are about 100 lines of code, so it's maybe time to reorganize, but yeah, we have 1 hour and a half. Okay. Yeah, and now if I set this to not minus, but the other one, I get, yeah, that's cool. Or the mean if you want to see the real ball moving. That's a little, yeah. Oh. Yeah, that's the other issue with shaders. There's not really a way to debug things. The only thing you can do is see pixels. So sometimes if it goes black or white, you get, where am I? Okay. So what I showed before, I don't know if you know Inigo Quilez. He's the creator of Shadertoy. There is this web page where you can do shaders in the browser, and people do crazy shit here, like demo style shaders, stuff like that. He works on for a long time in Pixar, and then I think he's at Disney now, and he's doing, for example, these images in 1 pixel shader, right? Which is just mind blowing, yeah. We're almost there. He's really, really good. He has a new one from a couple of days ago. I mean, this one is really nice as well. Yeah. He has this one from a couple of days ago.
Oh yeah, we see it on this screen. Everyone gather around.
Oh,
It's so bizarre.
why?
I've never seen that before. I don't know.
And yeah, shit, I'm talking here to myself. Well, then Inigo Quilez.
Oh, it's like doing copy protection.
Oh wow, pretty amazing.
Because it's flowing into like a video.
Yeah, HD, yeah, yeah,
Looks like it's
yeah.
If some step doesn't pass that on properly, it just
Oh wow. Well, it's this guy. He has some interesting talks, like this one. Again, sorry, I made a mistake. This one here, where he talks you through the math of doing Raymarch hard that beats. It's really nice. Well, whatever. He has many articles, and one of them is about distant functions, how to do, for example, a sphere. That's the same one we did, right? That's the same line of code that we use. How to do a box, a little bit more complicated, a round box, torus, and a lot of stuff. That's really nice.
What's his name?
Inigo Quilez. He's from Basque Country in Spain, but has been working in um, Pixar for forever. He's the shader master basically right now. Well, right now for since yeah. And so you have primitives, how to draw all these shapes. For example, let's take this one or whatever you want. I'm going to take this one, octaedron, and I'm going to copy it and should be good to go. Yeah. So now I'm going to call a new octaedron, call it octa equals sine distance octaedron
Was that under code?
p distance functions. In articles, distance functions. Yeah, he has a lot of stuff published. And just pick one. I mean, there's some of them that they are more tricky, but pick one, put it, and then P and this, whatever. I think one should be fine. And then we can combine those. So
We're
for
not finding the distance functions page.
no? Oh, now we need it. Yeah. So it's Articles, Control F, this distance functions, 3D distance functions. Oh, yeah. Sorry. Sign distance functions. Signing meaning it will tell you if you are inside or outside the shape. That's useful sometimes. I mean, yeah. So pick one. I went for the not exact octahedron because it's short, just because of that. And I paste it, and now I'm going to use it. So I had my spheres. Now I defined my octa, and I'm going to place that as a mean as well inside. Same thing, if I want to position my octahedron, I can just do it. One, yeah. So now it's there. I'm going to call it minus. So I'm just playing around a little bit now. And if I change that to max, now I get a little funny thing. And if I bring it a little bit to the front, maybe a little bit more, then it's gone. So 0.7. Let's try with minus, just as I said, playing around. Okay, I'm going to come back to minus, to minimum, sorry, so we can see it. Okay. So that will be the way to add more elements to our scene, right? And now if you take a look here, down, then there's primitive alterations. They are all really cool. This is what we are doing, the combinations. There's a smooth union that's really nice. I love it. Because yeah, it does this scene like metaball style. It's really cool. But where I'm looking at for, this also is really nice. Repetition. That's the one I said that it's almost for free. I said at the beginning that was almost for free to make repetitions of the same um, uh, shape because all you do is a modulo. It's one line of code and you get infinite numbers, infinite copies of the same shape, basically. This is the one. Displacement. That's pseudocode. That's not real code. What we're seeing there is that the primitive gets added to a displacement of the same point. What we can do instead of that is what we did this morning. That is deforming the space. So if we deform the point at where we are sampling, we are effectively deforming everything, the world, basically, the map. So we're going to do that. So we're going to do it only for the octahedron, okay? So what we're doing here is saying that my position is going to be, let's start with multiply, be multiplied by TD, how is that? Simplex? Perlin, let's go Perlin. Perlin noise. I'm going to make a typo here for sure. Yes. So now our octahedron, that is the same formula, is different because we deform the space where the octahedron lives. That P is now twisted. Let's bring it down. That needs to come really start to see. So instead of that, let's go with a plus. Yes. And I'm going to move this sphere a little bit more to the side so we can see what we're doing. Or do you see that? So to the position that we were sampling at, I added a noise. So I deform my ray, basically, is what I'm doing. So now my ray, instead of going in a straight direction, I'm deforming it based on a noise. So then I'm getting weird, warped results. I'm going to try with simplex. Nasty. Yeah. So now that we'll have a scale or frequency for our noise, we can also add an offset. Right? That will be to move our noise. Bear with me. This is a moment where we all get lost. So what I'm going to do, we have a noise. We have a scale. That means the frequency of the noise. And now we have an offset. What you do normally when you place noise chop, first thing, uptime dot frames, right? So the noise moves. So you don't have something static. That's what we are going to do. But inside of the shader. So I declare a uniform that is a float and it's called time, right? So I'm going to give time to my shader. Then I go to my top. I need to declare it. And I can absolute time dot frame, and I'm going to make that slower because I know already that's too much. Times 25. You all know how to do that. Declare a variable, an uniform, sorry, set it in my parameters in vector1 tab, and animate it with an uptime dot frame. Take that away, and now I can use that inside my shader, and this is a number that is going to move. So instead of an offset of 0.1, I can use my time. And as I said, that's way too fast, so I can also zero zero 0.05 maybe. There we go. Yeah? I'm going to move my plane to the top because I don't want to affect that one. And now I'm going to move my noise here up. So now it's going to affect also the spheres. But I'm not convinced, so I'm going to bring it back to where it was. Yes. And now one last thing, and then we play around with it. For Jacob that asked for it, light position. Now that we have time from outside, we can use it to animate other parameters. For example, my light. I can add to the position. Oh man, there we go. To the position of the light, I can add another value based on that time. That will be basically the cosine of time for x, the sine of time for z, and we set this to be way smaller, 0.05, and this one as well, 0.05. Is that 0.5 enough? Tweaking. At the end of the day, this is where you spend most of the time. And I'm going to make it a little bit bigger. Yes. Have you seen that one? So what I did there, my light position, now that I have time variable that I can change or animate stuff with it, I'm just changing my light position in the XZ plane. So basically this plane, I'm orbiting the light around the center. Nice. Yeah. Yeah. So exactly. So let's actually do the opposite of. Oh, what was that? I'm going to make a sea of red stuff. So moving my things around in the map, I can break it. What was that? 051. Where? What did it break? What? Okay. I'll try once more. So what I want to do is instead of affecting my octahedron, I'm going to leave that one quiet here up. Man, I'm losing my save. Okay, the octahedron is now out of the noise. And after I'm deforming my position, I'm going to paste my plane. I move the plane after the noise and the octahedron before the noise. So what I'm getting now is a C style deformation. Yeah, yeah, I see it. Not sure. Probably there's some absolute value somewhere that we should take care of. Let's try with Perlin if we have the same. We do have it, but it's less visible. I changed the type of noise. Yeah. Probably, yeah. I mean, the loop is expensive. The Raymarching loop, it takes. And the more things you add, the more it takes to calculate the map. So, yeah. The, um, the idea now is that we have something that is a little bit modular, meaning we get our lighting in a function that is outside the main program. So we can create different lighting models that we can apply to this same algorithm. So the Raymarching part, you can leave it how it is, and then you can research a little bit, for example, on fong lighting and use that one instead of this diffuse lighting. So you can use the same code base to create new looks. Same with your map. We have a map that is separated from the rest of the code. You have it in your functions. You can add whatever you want over there. For example, this octahedron that we copied. So it's semi-modular. It's all about distance functions. Yeah. 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 That's very, yeah, that one is really complete, and he's adding more. Like he adds from time to time. He's a researcher in mathematics, so he finds from time to time new stuff. Like for example, before he only had this not exact function, this sign distance. Now he has it exact, meaning you can really tell if you are inside or outside of the octahedron. Yeah. No, it returns the distance with a sign. So a negative distance will be that you are inside, how far, and a positive, yeah. I guess it's the moment for you to play around a little bit. So to make some uniforms, move the shapes, try to put some noises in another places, check different combinations of min and max to combine things, try to add things, like break it basically. Yes. Are you playing around with the thing a little bit? Um, One thing I will do is to copy um, the smooth union from Inigo because I really like that one. So I'm going to copy it here. Woohoo. Sorry? Yeah. Yeah, that's the way you combine. Yeah.
So like, if in your whole thing you had 50 shapes, you would somehow have to do min and max for every single. Okay.
Yeah.
Gotcha.
Yeah. So you have 2 or 3 ways to combine things, and you just have to. Yeah.
Put those in a loop and just like somehow I'm wondering how you could possibly write all of that if you had a bunch.
Yeah, simpler. Yeah.
Oh, okay.
No, at the end of the day, what I do is always, yeah,
Okay.
I keep adding. So I don't put them like there, all of the like here, mean of this and that, because I got lost. I always do one mean, one max, one mean, and then
Yeah, I don't accept the and.
yeah, yeah, because there's one that are written in pseudocode and others that are written in code. So when it asks for the primitive, you have to rewrite it in your own way, because we don't have that as a function or primitive. What we have is a map only. No, no, you just rewrite. You're talking about the repetition, right? Um, yeah. Um, yeah, actually, it's just this line, the interesting part, right? And what you do, for example, is to bring that to where? Mm, so let's create a new one. Vec3q equals this is P, that's correct. And C, how was that again? C, that means, what means that? That's space, probably. So we should make a new one. Vec3 C equals vec3, let's say 10, 10, 10. I don't know, let's try. Okay, we have Q, and let's use it maybe for the octa. So instead of P, I'm going to connect Q. Yeah. I'm defining C. I gather that C is the space in between them. Yeah, looks like. Yeah, that looks legit. So it's a domain deformation, right? What we're doing is repeating our position, similar to what we did this morning with the tiling. Ah, And it's looking weird because we have a smooth union, of course. So it's trying to, well, let's take it out. So let's do just mean. Yep. Hmm. Yeah, but then you have to define Z. You don't have it defined. Well, just a line above, like I did here, vec3Z. I just, yeah. You remember your light? We have a 3. If we put that more away, yeah. So that T that we define is basically how spaced the repetitions are going to be. So we can say that in C, they need to be more spaced than in the rest, for example. I leave you playing with it a little bit. I'm going to go around and check on you, like how you're doing, if you have questions individually. And then we check how to combine these with subs, like in one image. Okay? Compositing, combining the depth from both. Yes. Where? How can I do that? That smooth union, I took it from Inigo and the octahedron as well. And then you have to use it. So what we did there was to create a copy of our P, our world position coordinates, and we deform it with a mod, right? So we repeat it in space, and we call that Q. And now you have to use it. Yeah. So I used it in my octahedron, for example. No. Yeah.
Well, in touch you get the info.
Well, the info, but in logic, to test your logic, the only way is output in pixels. So that's the only way you can really test. Yeah. Yeah. It's too big. Yeah, because it's too big. Yeah. It's too big, probably. Be- I think the smooth up should go. Yeah. I think K shouldn't be bigger than 1. I think it's a range from 0 to 1. Hmm. Yeah. Or a remap or minus 1 to 1. Sine. Hmm. Main is not that big, as you can see. And actually, we should take out the loop into a Raymarching function, and then main would be super clean to look at.
Go back up to the.
Yes. To where?
I want to see where you're doing the repetition.
Um, mm, mm, mm. And then I'm using it here, right? I'm just making a copy of the P of my position. I'm deforming it, same way I'm deforming my noise, and then I'm using it. So the next steps here for you to take will be make a nice lighting model that accepts more than one light. Then the next one will be to use texturing to do like we are UV less right here, so you should go with a triplanar texturing technique. Um, yeah, those will keep you busy for a while already. The next steps I'm saying for you after this one will be to check another lighting models, for example, Fong, and how to apply them here. And then after that, how to use textures as well. Like a triplanar mapping will be, for me, the first thing to look at. And then environmental light, reflections, yeah. But before that, and before we leave, let's take a look on how to combine this Raymarching with subs. I'm just going to show you. Don't go crazy with it. I'm going to stop this one. So so this is going to open. That's an early example, like research we were doing for the design of the summit branding. And as you can see, I have this sphere noise here up, the yellow one. That's a sub that gets rendered in there. And I'm taking the depth of that scene, right? I have my light, my material, my camera, and then I'm taking the depth of that render. And I'm taking that into my shader. There's this one here. Let's open it out. Where is it? Uniform. No, that's a texture. I'm just sampling the texture. Raymarch. Here, depth. So in my main function, I'm sampling that texture, okay? It's an input, right? So I input the depth of my scene as a texture to my shader. And then, as we were doing before in the Raymarch, I'm checking against that depth and breaking. If my ray is hitting that depth position, I break. I don't return anything, meaning that will be alpha. Yeah? So if we take a look at that alone, comparing, you see how it's cropping Let's make that a little bit more. Oh, where I'm at. Transform P. There. You see how when that shapes intersect this one, just cut it out. I'm not rendering anything there. I'm just quitting the loop of the marching steps, and I don't march anymore, and I don't return any depth value, basically. And then another trick that I'm doing there is having two outputs. We saw before that we have our out frag color, and now I'm declaring a new location for the depth. And I'm outputting at the end of my main function. I have two outputs, color and depth. And you can see them here inside. In my render select, I can select the second that's here, color buffer, the number one, that's the second one. I have to say in my GLSL top to use two buffers, not only declaring them in the shader, but also allowing them to go out in my top. So I have a black and white, like a mask, basically, that I can use here to get that image that you see and combine that, just compositing out with my rendering. So at the end of the day, I'm just compositing in screen space because a Raymarch is not more than a fragment shader. So it happens in screen space. The next step will be to make that shader have uniforms for the position of the camera and connect those positions to this camera and have a matrix with the projection view and all the stuff. But it wasn't worth it for that experiment here. So that will be the way, the easiest or the simplest way to go for combining scenes renders in Touch with SOPs with Raymarch stuff that you did yourself. Yeah, a simple version. I can replicate that technique in the other one. Yeah. Yeah, of course. As well, I'm testing both. Yeah. Yeah. Where is it? Yeah, here. Well, this is a different type of Raymarch where I have a heat and the materials and yeah. But yeah, basically I'm testing against the depth and then max distance as well. Yeah? Thank you. But let's play with this one. What I will do, I guess, is now is dirty. I will change my positions. Boop. Hmm. I yeah. Mm. Mm.
So then instead of putting them farther, they're like the same amount of repetition, or like that makes sense.
And then let's make a copy. Yeah. Say it again. Yeah. Yes. Our ray origin is the camera position. From there, I'm throwing rays to the screen, meaning to every pixel, and then I march through them. Yeah. No, you need a matrix for rotations. Like if you start to use rotations and positioning, then you need a matrix. Yeah. As we were saying before, I will go with having the camera position external and then controlling that from outside as a uniform. Yeah. Yeah, yeah, yeah. As the rotation, but to combine those, you need a matrix. That's what I'm saying. Like we can take a look at the one I had. Oh, sorry. Um, so I have it in this one, for example. Um, this guy. No, actually, yeah, that's smarter. Just with a cross product, actually. And for rotate individually in angles, as you see, matrix is what you go for. Yeah. And you can externalize those. These are not, but you can have it them. You can have them outside, and just import for every project that you're using Raymarch. And then, of course, doing your container and making parameters to really make it modular. Yeah. Like I have the look at camera here, for example. So if I go, so it keeps looking at it. based on the so the no, not the ray. I'm moving the camera, but keep looking at where I want. I'm adding a rotation to the camera basically. Look at like the same as in the Unity camera. Hmm. A good trick of that one actually is where's my map? Here, I have a loop in the map. So what I'm doing basically is a little fractal. And you can see that this is the same shape repeated and make it smaller. So I have two shapes in a kind of a fractal loop. So they got smaller. You will see, yeah, here. They are the same, just repeat it and make it smaller. Yeah, yeah. Yes. No, I should totally do that. Yeah. Basically, just bring in the other shader here. That system is there. Yeah. It gets warm. I mean, the laptop gets. Yeah. Sure. Yeah. Of course. Yeah.
It's gonna take a lot though. Computer would shut down before you fry it.
Hmm.
How would it, like, would you get some sort of indication from your computer that things aren't going well?
Yeah, like your CPU will feel it before it fries, and it will shut down probably. But I mean, I've seen it. Okay, it happens. Yeah. If you're in a really hot venue in summer under the sun in Spain,